Hello everyone. I'm Jason Xin. I'm working at Tencent, responsible for the troubleshooting in the networking area. So welcome everyone to join my presentation. Honestly, I'm getting cold feet to address it in public. It's my first time. Okay. This topic will be chopped into five parts. The first part is a brief introduction. I will show the use case might be and how you use it. And the second and third are the past and the present of the socket timestamping. And the fourth one is I'm going to introduce the BPF timestamping, which I'm recently working on it. And the fifth is how to extend more of the BPF timestamping feature. I would like to shift our focus more on the stack and the kernel itself. Okay, this is the brief introduction. As William said at the netdevconf a few years ago, the timestamping is the key to debugging network stack latency. I attached a figure to demonstrate how it works in the real workload. It's just an example. The use case of database goes like this figure. As you can see, it is evident I only deploy the feature in the server side. I would highly recommend that you deploy the feature on both sides. With this feature enabled, you will record the timestamp consecutively. The first timestamp you record is the X software. It is the timestamp when the server side receives the request from the client, and it will record the current timestamp. It is near the same as the TCP dump works. And then we will ask the application to record the timestamp before calling send a message. Send a message is call, and you can calculate the delta between each of them, and you will see if the latency issue occurs, and you can say, okay, it's the application's problem. It's not mine. The reason why I drew this figure is that we've encountered numerous issues reports that are reported from our customers, and they say the application engineer who cares about the latency comes to us or comes to the network operator and say, hey, we got a problem in history. Can you take a look at what happened at 2 a.m. o'clock? No one knows that, and sometimes we will come to the network operator and say, can you take a look at this? But in normal cases, the answer is no. So we have to deal with this latency problem. Okay, the past and the present of socket timestamping. Back to the 2009, the Patrick Oley, who were working at Intel, finished the first edition of socket timestamping, and he completed the basic framework of communication between the kernel and the user space. In this first commit I listed here he explicitly distinguished the use of a data path and the control path. The generation flags are used in data paths to tell the kernel, can we generate a timestamp when the key be transferred to the certain measured point, and how about the report flag? If without the report flag, application cannot receive this timestamps. I will talk about more about it later. Okay, and I drew a picture that demonstrate how it works. The first step is you need to set a socket opt to the socket, and then application tries to send a large amount of data, and that will be passed to the UDP layer and the DevQ XMID and the SATA XMID and to the hardware. In this first edition, he only implements the software and the hardware timestamp. At these two measured points, the current timestamp will be generated and allocate a new SKB. And this new SKB will carry the timestamp and will be put into the tail of the arrow queue. And then we will ask the application to call the actual receive message to receive these two SKBs from the arrow queue. It is how it works basically. Let's go into more details about the socket times. In 2014, William completed and fulfilled and enhanced the whole feature for the TCP and for UDP. And we can see this figure is much more complicated than before. We have more hooked point like the DevQ XMID. It records the timestamp when the SKB is going to be enqueued into the queue disk. We will record that timestamp. Okay, and the second important thing is the TSK. TSK is used to correlate the sender message with the SKB. If TCP send amount of data, that will be split into multiple smaller size SKB. When the SKB goes into the queue disk, we don't know this SKB belongs to which sender message, so we need to use the TSK to identify. Okay, the current status, like Google. They developed the Fathom, which is implemented based on the Dapper of many years ago, and more and more hardware supports the timestamping, and I don't remember the name. The new usage of TSK for UDP was merged last year, and I hope the TS completion feature is coming soon to support those hardwares that cannot generate the PTP hardware timestamp. And last one is BPF timestamping, which I'm currently working on. It's halfway done. Okay, let's talk about a little bit about BPF timestamping. The reasoning behind the BPF timestamping is we truly encountered several problems when we try to deploy this feature in production. The first one is we have to require the application to change their code. It is obviously not acceptable for our clients. So we have to resort to other way to use this feature by writing a kernel module, for example, and that's what we've done in recent months. And the second one is it introduced the system overhead. As we can see this figure, the red boxes. If you use this feature, we have to ask our clients to modify their codes to add more extra receive message. If you have 3 generations flagged, such as the DevQ XMID, SATA XMID, or hardware timestamps, we will add 3 extra receive message respected to receive the SKB from the arrow queue one by one. So it will cause the performance degradation. It was mentioned in the earlier Netdev conf. And the third one is the UAPI compatibility. I'm starting to say we still not fix this because of the nature of BPF. I've proposed a question the day before yesterday when Alex gave a presentation. Sorry, and little flexibility. Little flexibility means if you want to know more about the stack, such as those fields in the struct TCP info, we have to change our code and upgrade the kernel. It means we have to wait at least a few months or years to let our customer enjoy this new feature. So it's not really acceptable. Okay, the background of BPF timestamping feature. Actually, I've talked a little about the reason behind this. I'm encountered by numerous reports from internally, so we have to deal with it. Then I resorted to this feature and try to deploy it rapidly and try to transparently equip the application. So we wrote a kernel module, and then last year I proposed this idea and discussed it at Netdev, and I received a few brilliant feedbacks from John and William, and we then finally reckon BPF is the best way to go. So here we are. Many thanks to Martin and William and John and Jacob and Vadim and everyone who reviewed this patch. It took us almost 5 months to get merged in the kernel finally. And many thanks to my colleagues for helping me wrote those kernel modules and deploy it in production. Okay, let me quickly go through the details of implementation of BPF timestamping. The first step is BPF sort stack object, which works very similarly to how the socket timestamping. You have to call this BPF sort socket object in BPF program in the initial phase, like the TCP init transfer. There are 2 BPF callbacks there, so you can. And isolation. Isolation means we support those 2 modes of timestamping work in parallel. It means that if application enables the socket timestamping by set socket opt, that does not mean we cannot use the BPF program to enable the BPF extension. And the correlation. Let's revisit a little bit about how the socket timestamping works. If you want to use the socket timestamping, we will require the application to add the to record the timestamp before calling the send message. So in BPF timestamping, we don't want to our application changing their code. So we have to do it on our own. We use the F entry to hook a TCP send message logged, for example, and record the timestamp. And then we will call this new callback in this figure to do the correlation, to correlate the TSK with the SKB. We will go into more details if someone proposes questions on this. I'm afraid I'm running out of time. And we introduced the one generation flag for the socket timestamping. We have multiple generation flags versus 1 or 2 report flags, and here we use 1 or 2 generation flags versus multiple report flags. Report flags here are the same as the socket ops callback. We also support the selective sampling feature, which was proposed by Jacob, and it works similar to the same message stat in socket timestamping. We will allow the application to start measure those flows and stop and start over again, something like that. And the tutorial, I believe I'm already stated it very clearly. And let me rephrase a little bit. The first step is please use the BPF set socket to enable the feature, and then we will finish the correlation. And the third is we will record each timestamp and calculate the delta between them, and we'll find where the high latency occurs. And more details can be seen in these self-tests. And then there are 1, 2, 3, 4 noteworthy points. The first one, we are running out of TX flags in SKB. William just has recommended one to prepare for the upcoming TX completion feature, but I'm going to implement the remaining part of BPF time stamping, like receive part on the receive part. So I have to introduce another one. That means I have to reclaim one more time. And no lock protection. If I remember correctly, Eric once mentioned this. Everything, those fields we extracted from the structured socket are not protected under the socket protection. So that information might not be that inaccurate. And what are left to complete in BPF time stamping, UDP support or the receive path support, I believe I will finish in the first half of the year. And the last one is UAPI compatibility. Still remains, I'm sorry. And how to solve the interference impact issue? I will. Okay, what is the interference impact? Let me see this figure. Supposing there are 10,000 flows established in the running machine, we only want to trace one of them. By writing a normal BPF tools. It means the rest of those flows will face the same situation as the one we are going to chase. They will all the 10,000 flows will encounter the same problem, namely the performance degradation. It causes a little bit impact. So what can I do to solve the interference impact? So I prefer the BPF time stamping. It's like an advertisement. Okay, and we can see in this green box here, that is what we wrote BPF. This is the place where we wrote a BPF program here. It means the rest of the normal flows will not go into the green box, so it will not be impacted because of the BPF program, but there remains one place in the TCP send message logged function, which I truly use the F entry to hook this. So I'm going to fix that. Revisit a little bit of how we use the F entry, and let's take a look at this black picture. The code snippet shows that we use the F entry to hook this point. And I like the F entry feature. It is very lightweighted, and it only replaces a few bytecodes of the certain function. But lightweighted doesn't mean it's zero cost. The F entry impact, if you do nothing in the TCP send message, like this figure illustrates, and running netperf by default on the loopback, you will see the 4.6% decrease in performance. So it cannot neglectable in production. And if you try to compare the 4 tuple, something like that, you load the socket address or socket port, it will increase this number to 7.1%. And how we can avoid this F entry impact? Of course, we can insert a new time stamping callback here, and then it will look like this. So the normal flows, the unmatched flows, will not go into those green boxes, and they will work normally as before. I don't have how much time do I have? So I will quickly walk you through the next feature I'm going to add, the tracing every SKB for BPF time stamping. The current flow of the TCP, it works like this. If you send send a message, it will tag this single SKB and will have corresponding timestamps when it enters into the different measure point. But if an application tries to send a large amount of data that will be stipulated into a smaller size of the SKB, only the last one will be tagged. So that means only the last one SKB goes into the different points, and then we will have a corresponding timestamp for it, only the last one, And for UDP, it only records the first one. Yeah. So this is how it looks like in the future. We will record every SKB of this feature. I think I will skip these details if you will have questions about how we can implement this. Okay. Let's talk about more about the merits and demerits. In production or in real workload, I highly recommend not to use the tracing every SKB because no one can afford to pay so much storage to store so many items. Like at Google, they do the selective sampling to avoid too many storage costs. But can we shift the can we use it for the one-off deployment, or we can use it as a debug tool like the Redis? We can search it in the GitHub, and we will find out there are some existing repo like the netcap or nettrace. We can use it for the basic analysis locally, not in production. I mean. So with this feature enabled, we can clearly see the delta between each stages. So it would be super useful for if you want to test something, you want to reproduce it locally, and you will see how it works in the kernel, and you can observe the behavior of the stack. Okay, now it's time to talk about the future of build timestamp. It's a little bit late, but I proposed a few questions here. The first question is, what is the end? Can someone tell me, okay, or we can stop here and we don't want to add more features because it's totally enough for the current troubleshooting area? Or at least one explicit question, can we add more hooks in the TCP write execute because we can see some SKBs get stuck in the TCP layer because of various policy of flow control, like the TSQ or Negro algorithm. I don't know, but I would like to try this. And the second one is it possible to replace TCP dump in the future? Because we have a much more valuable information than TCP dump has. TCP dump only records the timestamp when the SKB SKB is about to send to the driver. So we have that timestamp as well, and we have more timestamp than the TCP dump. So can we do it? I don't know. And a few days ago, Brighton sent me a paper that describes exactly what I've been doing. I can show the title of the. Okay. The title of the paper is How to Diagnose blah, 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 blah. And it says once the lifetimes of messages are constructed, they can be compared to identify anomalous processing that led to their latency deviation. So that is what exactly we do in production. We compare the different kernels. We compare the same kernel in different virtual machine or something like that to compare between them and to see if there is room for optimization or if there is something not right. Can we fix it? And after that, with the tracing average KB feature enabled, and can we explore to leverage the numerous real data? I assume it will be super useful, but I don't know how to use this massive amount of data, such as by AI. I don't know. So it's an open questions. Thank you, everyone.
Questions?
It could be a tough question.
Is it better? Yes, it's better. Yeah, about the question about can we add more hooks? There is a hidden feature about hooks. It's NUP, yes, but the compiler is forced to keep around whatever variable your hook is entered in to use, like a trace point. So it has some side effect on the generated code, even if the trace point is not taken. That's something that most people ignore, but it is real. Something very simple. There is a IRQ trace, which generates an event whenever we mask the hard interrupt, right? And so if you just look at the code, which is generated, it's very stupid. Like we do a push flag, and then we pop the flag in the stack, and then we read the stack into a register just in case the hook is going to be called. And this write followed by the read is a huge store point on many CPU. So that has an effect. So just to answer your question.
I totally agree with you. We are writing a kernel module to implement to try to implement something like that, adding more points. But we see the performance degradation, which was beyond our imagination. So. Yeah. Any question?
Well, if there are no more questions, thanks, Jason. Your first presentation?
Yeah.
Is this the first time for you to present anywhere?
Yeah, it's my first one.
Well, congratulations, you did well. Thank you.
Thank you, everyone.